This is section 5.8, inverse trigonometric functions, integration. All right, having just learned how to do the derivatives of the inverse trig functions, it would make sense that we would then move to antiderivatives. So, of course, they pair up nicely, but I do want to say that because the derivatives appear pairwise, and the only difference is a negative sign, like the derivative of arc sine of x is 1 over the square root of 1 minus x squared, and the derivative of arc cosine of x is the opposite of that, negative 1 over the square root of 1 minus x squared. What we typically do, because the antiderivative of those would be only a different integrand by a negative sign, typically in the antiderivatives we typically only use one of these two, and for the other two pairs we use one of that pair. And so because it's the positive one and we won't have to deal with that negative sign and trying to remember when to include it or when not to include it, typically what you should do when you see an antiderivative of this form that you're supposed to do, pick the arc sine or sine inverse, and that'll be the one that you choose. So don't use negative cosine inverse for that. And if we all abide by that, it makes looking at these easier and easier to deal with. So if you look at theorem 5.19, you'll see the antiderivatives. Notice that we only get antiderivative answers for the inverse trig functions of arc sine, arc tangent, and arc secant. Those are the ones we'll get. Notice that the formula involves an a, which is a constant, so it doesn't have to be 1 minus x squared. It can be any number minus a function of x squared, where u is just a function of x, and then the du, of course, is part of that. So we'll have to make sure we have the derivative of that inside function. A couple of things to notice. 2 of the 3 have a 1 over a in front of the arc tangent and arc secant. Arc sine does not have that 1 over a. They all involve an argument of u over a, except for arc secant. You're going to have an absolute value of u over a to contend with. So as you memorize those antiderivatives, make sure you are clear about what it is. Does it have 1 over a in front or not? Does it have an absolute value of u over a? Or is it just u over a? Okay, so let's do some examples. Excuse me. So if we were looking at the integral of dx over the square root of 4 minus x squared, it's pretty clear that the constant there is a 4. So that means that a is the square root of that, 2. And in this problem, u and x are the same thing. So du is dx, and we don't have to introduce any new constants to make that work. Now, the other thing, if you look back at the antiderivatives, pay attention that the square root of a number squared minus a function of x squared in that radical position in the denominator is very different from number 3, which is u squared minus a squared, a function of x squared minus a number, with a u out in front of that radical as well. So be careful that you don't conflate those two accidentally. This is the a squared minus u squared, so this is number 1. And so this is no 1 over a, right? 1 over a does not involve, is not involved here. So inverse sine of u, which is x, over a, which is 2. And then, of course, don't forget your constant of integration. B. This one is dx over 2 plus 9x squared. So notice this is a sum, and there's no radical. The only one that looks like that is number 2. Now for that one, be careful. A squared plus u squared and u squared plus a squared are identical. So the number could appear first, as the formula says, and this problem has, or it could appear second, and because it's addition, the order in which you write those would not matter. So it does not have to be number plus u squared for this to work. Okay, so our number, our constant here is 2, which means a is the square root of 2. And u squared is 9x squared. So u is equal to 3x. And if u is equal to 3x, du is equal to 3 dx. Now, of course, we don't have a 3 dx, we just have the dx part. So we're going to have to introduce a 3 and a 1/3 to make this work out correctly. So this is 1/3 times our integral of the form of the number 2 in that theorem. So that one is the 1/3 that we had to introduce times 1 over a, so 1 over square root of 2, times arctangent or tangent inverse of u over a, so that's 3x over the square root of 2 plus c. And this one I would like for you to simplify the radicals involving numbers always. So that will become 3 square roots of 2 over 2 inverse tangent of 3 square roots of 2 x over 2. Make sure that x doesn't look like it's under the radical. It's definitely after the radical has ended. All right, so that is the answer to B. Let's look at C. We have dx over x times the square root of 4x squared minus 9. And which one of these does this one look like? Well, it looks like number 3, because we have the functions minus a number under the radical. And we do have an x out in front, so that's looking even better. So that means that our u squared, and you are going to be governed here by the thing under the radical, not the thing in front, to find u. So be careful. It's the u squared is 4x squared, which means u is 2x. So because u is 2x, we have to introduce a 2 so that that's really u in front of the radical, which means since that's 2 is in the denominator, we'll have to multiply by 2 out front, which you can think of as 2 over 1, so it's in the numerator. Okay? Then du is 2 dx, and then I think, oh, well, that was dumb. That 2 I wrote outside actually is needed inside. So if I'd been smarter, I would have looked ahead, but that's okay if you don't see that right away. And if you don't do what I'm doing now and erase that 2 outside and move it back in, you can always multiply by 2 here and times 1/2 outside, and the 2 times the 1/2 will become 1. So no big deal. Either way, it should work. But right now we have the du over the square root of u multiplied by the square root of u squared minus a squared. And we haven't talked about a squared yet. A squared is 9, and so a is 3. Okay, since we're using number 3, this is going to be 1 over a, 1 over a, times the secant inverse of, or arcsecant of. Be careful, this one's different. It's the absolute value of u, so the absolute value of 2x over a, which is 3, plus c. And you can simplify this sum. I would probably leave it like this. So I'm going to put this as a parenthetical statement. The absolute value of a product is the absolute value of one factor times the absolute value of the other factor. And the absolute value of 2 is 2 over the 3 multiplied by the square root of x. And since we don't know if x is positive or negative or 0, that absolute value has to stay on it. If we decide to take this that far, that would be the appropriate final response if you're trying to simplify your answer as much as possible. But like I said, the original answer I have there is just fine. So you may leave it in that form. Okay. Now, because our denominators have squares and difference of two squares, completing the square will help a lot. If instead of seeing a difference of two squares, for example, you see a quadratic polynomial, you might need to complete the square in order to have it in that particular form. So just as a reminder of how you complete the square, let me make up one here where I want you to complete the square. Like if I had 3x squared, I have to think this through, so pardon me if it takes me a second. Let's see, let's make this minus that plus 48 back here. I think this is going to work. I always hate making them up on the fly because I'm afraid I'm going to make a mistake. Let's see. I hope this is going to work. No, I just saw my mistake. Hold on. Let's make this 24x and hope that works. Okay, so this is just a reminder of how to complete the square. To complete the square, the coefficient of your squared variable must be 1. So you're going to have to start by factoring out that 3. If the coefficient of x squared is already 1, then no big deal. You're ready to rock and roll. We're not completing the square. Darn. I messed up. Well, this is, after you've completed this square, this is what it's going to look like when you're factoring. We'll complete the square in a second with some other problem. So the factoring is the x squared square root goes first, the sign of the middle term goes in the middle, and the square root of the second term, the third term goes here, like that. So how did I get there? Well, I messed up and didn't really do what I meant. So let's complete the square over here with a different problem. Like if I had x squared plus 10x and asked you to complete the square, then to complete the square, what you should do, and if you look at the other example, you'll see that I sort of did this without telling you what I was doing and when I set it up. The thing you do once the coefficient of x squared is 1 is you look at the coefficient of x, find half of it, in other words, you divide it by 2, half of it, then square that result, and that's what you need to complete the square. So this problem up here needs a 25. Now, without changing the original problem, I wanted a 25 in there, but I don't want to change the value of x squared plus 10x. It's got to be equal to this. Well, the only way you can do that is using mathematician's trick number 2, which is add a form of 0. mathematician's trick number 1 is multiplying by a form of 1. Like when you have something like, there was a problem a second ago. I'm going to use it. Oh yeah, the radical thing. When I had, oh, I just saw a mistake up there. I'm glad I looked back at that. Wow. That part B, that's a mistake. That 3 was not supposed to be in the numerator. I magically made it go up there somehow, and it was wrong. So let me fix that. And so I'll have a 3 times 2 in the denominator, which will make that 6. And I'll show you the work that you go through to get that. That'll be my example of how I proceed. Boy, am I glad I looked at that. Anyway, we had 1 over 3 square roots of 2. And one of the mathematician's favorite tricks is multiplying by a form of 1, which is square root of 2 over 2, square root of 2, which won't change the value of what you started with. And so you get 1 times square root of 2 is square root of 2. 3 square roots of 2 times the square root of 2 is 3 square roots of 4. And the square root of 4 is 2. And this is a lot of extra steps that most of you don't need, but the thought process is what I'm trying to show you. So square root of 2 over 6 is what I should have had originally in that. So yeah, sorry about that. I think I was looking at the 3x over square root of 2 when I did that, and that does have a 3 in the numerator. So I think I looked at that and messed up. So I apologize. Anyway, back to what we were doing. We just added a form of 0. So these first 3 things, this trinomial is what factors. Like I said, it's the square root of the first thing, the sine of the middle thing, the square root of the last thing, quantity squared. When you've completed the square correctly, that should be the factoring. And then that will leave minus 25, which you can probably see now that's a form of u squared minus a squared, which would lend us the ability to deal with this problem if it fits one of the forms that we're talking about for the inverse trig antiderivatives. Okay, so let's look at another example. The integral of dx divided by x squared minus 4x plus 7. Okay, well, at first glance, I just look at this thing, I think, well, does that trinomial factor as is? I can't think of any factors of positive 7 that would add to negative 4, so that's a dead end. And if I tried to let u equal that denominator, the du would involve 2x minus 4, and I don't have a 2x minus 4 in the numerator, so that won't work. So what we get to eventually is the idea, well, maybe I should complete the square on that x squared minus 4x part. Okay, I'm not going to ignore the plus 7. It's still part of the problem. I'm just going to put it at the end. So I'm going to insert a form of 0 in here to complete the square. So half of negative 4 is negative 2. The square of negative 2 is positive 4. So I'm going to add 0 in the form of 4, which completes the square, minus 4, which means I'm really just adding 0, plus the 7 that was already there. Okay? So the initial trinomial part of the denominator factors to be x minus 2, quantity squared, and then combining like terms, negative 4 plus 7 is 3. And that now looks like the form for the inverse tangent. It's the u squared plus a squared in the denominator. Notice that this is u squared plus a squared. I said earlier the order of those two and the order in which they're added doesn't matter. The form says a squared plus u squared, but that doesn't matter. Here it's not an issue when you're adding what order you add in. Okay, so my u squared, is x minus 2 squared, which means my u must be x minus 2. du, therefore, is equal to 1 dx, so just dx, which I have. So the introduction of an extra constant to deal with that is not needed. My a squared is 3, which means my a is square root of 3. So I think we're ready to rock and roll. This answer for inverse tangent, don't forget this one has the 1 over a, so 1 over square root of 3. Arctangent, or tangent inverse of u over a, so x minus 2 over square root of 3 plus c. And so that simplifies to be square root of 3 over 3 arctangent of x minus 2 times the square root of 3 over 3 plus c. All right, so there's that one. Let's see what the next one's going to be. Get the page to turn here. A second. There we go. All right. So the next slide is about the basic integration rules. Remember last time we ended with the review of the basic derivative rules. So these are the basic integration rules, and you should have every one of these memorized. Most of them are things you've done a million times, it seems like now, so it's not as daunting of a task as you might think, but these basic 20 antiderivatives are ones that you need to be able to recognize and use correctly. So let's see what we can do using what we know from those 20. So let's just get a random problem here. So there's no guarantee what type this one is until we looked at it. It's not necessarily one of the inverse trig ones. Well, I say that, and then it looks like the very first one is not, yes, is that. It's actually one that we just recently learned. That looks to me like number 20. So our u squared is x squared. So u is equal to x. du is dx. And notice that I do have x in front of that radical as I'm supposed to, and I do have the dx, so no introduction of constants is necessary. And so this one should be, oops, I forgot to identify a. A squared is 1, which means that a is 1. So this is going to be 1 over a, so 1 over 1. Arcsecant, or in other words, secant inverse of the absolute value of u, which is x, over a, which is 1, plus c. And of course you would want to simplify that. That's just simply secant inverse of the absolute value of x plus c. Okay. Now let's look at the next one, b. So when you look at it, you got to look at it with the eye of, is this one of my basic forms? And don't get too stuck on it's got to be inverse trig, because some of these won't be. Just saying. I forgot to write the integral. There we go. Okay. Well, this kind of reminds me of the last problem, but that x in front of the radical is missing. And it's not in the order number minus x squared, so it's not number 18. So there must be something else that's going to work here. And I know I just filtered it through the lens of, it's kind of looks like an inverse trigonometric function. And when I see a radical with a function squared minus a number, or a number minus a function squared, I tend to think of those immediately, but that x in the numerator is going to throw that off. So let's see what we can do with this. Well, another thing I do with radicals sometimes is I write them, rewrite them in terms of powers, because sometimes that's helpful. So that that radical in the denominator gives me a negative exponent, and because it's square root, it's negative 1/2 is the power. And when you see that in that form, you may be thinking, at least I hope you are, that this is a u substitution problem. Let u equal the inside function. Many times when we see a composition of functions like something to a power, or the cosine of a something, or whatever, u substitution is our best friend in that situation. Du is 2x, then multiply that by the dx. So our du needs to have a 2. So I'm going to introduce that 2 so that I have inside the radical, I have exactly what I need. I have u to the negative 1/2 du, but I also have to introduce a 1/2 out here so as not to change the original problem's value. Okay, so if you can do this without writing it down in the form I am right now, that's great. I'm okay if you skip writing this step. But the problem that we are dealing with now is that I have u, x squared minus 1 to the negative 1/2 times du. And keep in mind, this and this together are my du. So all of that gets absorbed into the du. So using the power rule, the power rule says you increase the power by 1 and divide by the new power. The 1/2s cancel each other out, leaving the square root of u plus c. Then going back to the original variable, this is the square root of x squared minus 1 plus c. There you go, there's that one. Okay, let's look at c. Let me write that one down. Go back to that page. There we go, there it is. Okay, now this one looks hauntingly a lot like the ones we've dealt with. Because the order is u squared minus a squared in that radical, and there is no possibility of u in front of that, there's no possibility of getting an x inserted in front of that radical in the denominator, we can't use number 20. We can't use u substitution because, if you'll recall, we needed to have that x that was up there with dx in order to get our du. So u substitution will not work. And in fact, we can't do this one yet. With what we know, we cannot find this antiderivative. And it's very possible that, in fact, probably if you just randomly made up an integral, the chances are very good that you'd make up something that you can't integrate with what you know right now. Or perhaps even something that nobody can integrate. Some of them don't have closed forms, and so that's a conundrum that we will encounter later more. But this one, the only thing you could do is maybe have a algebraic, really strong algebraic program like Wolfram Alpha. Type this in and see what you get, and it won't be anything like what you're used to seeing. So for right now, you can't do this one. All right. Now I've added a few more. I hope I typed them in. I remember adding them. I don't remember if I actually went back and retyped them. So if they're not typed, these are brand new problems you weren't expecting. So Let's see what we can do with this. Okay. So this one can't use U substitution because our du would be 8x plus 16. There's no way we can get 8x plus 16 in the numerator. So I'm thinking of what we said earlier. I might want to complete the square. So what I'm going to do is the x squared and x part is the part I'm going to work with. That 25 is just going to be out there hanging out for a while, and it'll come back into the problem as we go. So the first thing is the coefficient of x squared must be positive 1. Okay, and I'm going to leave plenty of room there to complete the square inside of the parentheses. Okay, so completing the square, now that the coefficient of x squared is 1, half of the coefficient of x, half of 4 is 2, 2 squared is 4, so I'm going to add 4 to complete the square, but I can't just add 4, I need to subtract 4, so that in essence I've added 0 inside of those parentheses. So, oops, so this is 4, and the trinomial part of that I'm going to go ahead and write again, just to be really clear what's happening. Now, the minus 4 needs to come out of the parentheses, and when it does, it has to be multiplied by that leading 4 to come out of the parentheses, so it becomes minus 16. And then, of course, that plus 25 that's just been hanging out there waiting for its turn. So this factors to be 4 times the quantity, that's a plus sign, make sure that's clear, that's a plus sign, x plus 2, quantity squared, and then combining like terms, negative 16 and 25 is 9. Okay, so now this looks like an inverse tangent problem, which of course is number 19 if you want to look at that. So that means that our u squared is 4 times the quantity x plus 2 squared, which means that u would be 2 square root of 4 times x plus 2, the square root of x plus 2 squared. And so du is 2 dx. Okay, then our a squared is 9, which means a is 3. And we're ready to rock and roll, because we now have exactly everything we need to use number 19. So number 19 should be 1 over a. Oops, I'm not right. Hold on. I messed up. I said du was 2 dx. I didn't deal with it. So I'm going to have to introduce a 2 so that that becomes du and a 1/2 out in front, because I'm multiplying by that form of 1, which means that there's supposed to have been a 1/2 out in front of what I just did. Okay, so 1/2 from introducing 2 and 1/2. And then 1 over a is the 1 over 3 inverse tangent of u, which is 2 times x plus 2, over a, which is 3, plus c. And then we should simplify. We should get 1/6 inverse tangent of 2x plus 4 over 3 plus c. Okay, now I've got another one here. E is what I call this one. The integral of dx divided by the square root of 8 minus x squared plus 6x. Well, this one's making me think of the square root of a squared minus u squared. I know it's not quite in that form, so I'm thinking of number 18. So to get it in that form, I'm going to complete the square. This is a really major tool, completing the square. So make sure that you know how to do this. All right, to complete the square, the coefficient of x squared must be positive 1. So I'm going to factor off the negative, and inside of the parentheses I'll be left with x squared minus 6x. Factoring that negative off causes the coefficient of x to become negative. Okay, now completing the square, since the coefficient of x squared is now positive 1, half of negative 6 is negative 3, the square of negative 3 is 9, so I'm going to add 9 to complete the square. Then, so that I'm not changing the problem, I want to subtract 9 at the same time, so that I'm basically adding a form of 0. Now, that minus 9 is not part of the trinomial, and so we need to bring that out. And so that'll be 8 minus x squared minus 6x plus 9. And when that 9 comes out of the parentheses, don't forget it has to be multiplied by the number in front of the parentheses, in this case negative 1. Negative 1 times negative 9 means that it comes out as a positive 9. Okay, so simplifying means that we combine like terms, 8 and 9 is 17, minus, and then factoring leaves us x minus 3, quantity squared. And I think now we're ready to use number 18. So for 18, we identify a squared to be 17, which means a is square root of 17. We identify u squared as x minus 3 quantity squared, which means that u must therefore be x minus 3. And so du is 1 times dx. So we have exactly what we need to use number 18. And the answer, you'll remember this one does not have a 1 over a in front, so we'll sine inverse of u over a, x minus 3, over square root of 17 plus c. And if we rationalize the denominator, that becomes square root of 17 times x minus 3 all over 17 plus c. All right, and then the last one I want to do with you is f. In my notes, I called it f. And this one is the integral of dx over the quantity x plus 4 times the square root of x squared plus 8x minus 30. So I'm thinking that reminds me of number 20. So that means I'm going to need to complete the square so that the thing under the radical becomes u squared minus a squared, if that works. Now, it's possible that it won't work, so don't think that every one of these turns out to be a pretty problem. The textbook tends to make them kind of nice, but watch out. Sometimes they throw one at you that you can't do, like that C problem above. Okay, so I need to complete the square on x squared plus 8x. The coefficient of x squared was already 1, so I didn't have to mess with that. Half of 8 is 4. 4 squared is 16. So I'm going to add 16 to complete the square. Then subtract 16, so that I'm really just adding 0 inside of those parentheses. Then don't forget that minus 30 needs to travel along. Notice how I have to extend my bars, my fraction bar and my radical bar. Those are called a vinculum, by the way. I'm having to expand those because these are a lot longer expressions than I planned for. That happens sometimes. Okay. So this is x plus 4. Square root of the first 3 terms of that factor to be x plus 4 quantity squared. There's an understood 1 in front of the parentheses, so when I bring that negative 16 out of the parentheses, it's multiplied by 1, so it doesn't change. So I'll have that negative 16 minus 30, which is negative 46. And this is now ripe for using number 20. My u squared is x plus 4 squared. So u is x plus 4. Now double check that what you have in front of the radical is this. You might have to introduce a constant at this point to make it be this particular u that's in front. This one's fine, so I don't have to do that, but be aware that you might have to. And du is 1 times dx. So just dx. Which we have, and that's good news. Our a squared is 46, which means a is the square root of 46. That's as far as that one goes. So we're all set to use number 20, and just go down here. This is now equal to 1 over a, 1 over the square root of 46, arcsecant, also known as secant inverse of the absolute value of u, so absolute value of x plus 4, and x plus 4 is not necessarily positive. Like if x were negative 10, it would not be, so we have to leave it in the absolute value until we have a particular value to put in for x. Over a square root of 46 plus c. And to clean that up just a bit, we will get square root of 46 over 46, secant inverse of the absolute value of x plus 4 times the square root of 46 all over 46 plus c. Okay, that ends this lesson. I will see you in class.